So we've discussed logic gates. This is how a computer gets its brain. You have the operations AND, OR, XOR for the two inputs, and all of their negations, NAND, NOR, and XNOR, which is my favorite name. And then, of course, the one input one, the NOT gate, and then the buffer, which is not. So first, I will show you that this is all you need. These gates comprise the entire possible set of operations on one or two inputs. The operations on three inputs obviously have a lot more options, but once you get to three inputs, you're doing more complex logic that's specific to one application, and you're going to be doing custom circuitry, or using a computer program to do it for you. So really, 1 and 2 input is all you ever need to really think about. And then I'll talk about how NAND is the universal gate. You can do anything with a NAND. There are other gates you can do everything with, but NAND is the easiest to make. It's super simple, wonderful circuitry, and it's quite common. Now, why would you use one type of gate to make all the other types of gate? Wouldn't that actually be less efficient? Yeah, actually it would. Using NAND gates chained together to make other operations actually can be as much as 3 or 4 times as slow, but it's cost effective. You only have one type of gate. You can buy a bunch of them. You never have conflicting inventories. It's easy to wire up. It's easy to program. So once again, just like the war between parallel and serial, where parallel technically can get more data across at the same time, but a lot of the time serial is a better choice just because you can pump them through fast enough that the simpler circuitry is worth it. It's the same thing with NAND gates. Although it's quite common to use a mixture of NAND and NOT, also known as inverters, and I'll show you that. So first, some circuit symbols. You may notice a pattern here. So let's start here. This is AND, this one here. 2 inputs, 1 output. This is NAND. It's the same symbol, but it's got a little bubble here. This little bubble indicates inversion. It means whatever this is, it's the opposite. So the same here. OR, NOR. So this is and, or, not or. XOR, XNOR, which by the pattern should be NXOR, but XNOR sounds really cool, and it's easier to say anyway. Or you could look at it this way and say OR exclusive OR, NOR exclusive NOR, whichever way you look at it. That's for the 2 inputs. The 1 input, this is NOT, also known as inverter, and this is buffer. Now, we discussed buffer before. Buffer does nothing. Buffer is just input and output, and the output is the same as the input, but it basically works as a non-backflow mechanism. It only goes this way. So it's security in your circuit. And there's the bubble. It's the do nothing plus an inverter. So the inverter is do nothing plus inversion. So you see the bubble. Always remember the bubble on these. The bubble means inverted. The bubble is used in certain other cases, such as a Schmidt trigger, sometimes. That's an inconsistency because some people have a circuit diagram that reflects how the circuit works, and some people have it reflect logically how it works rather than physically. The actual function rather than the construction, because you can get the same function from different constructions. And as usual, people couldn't agree, and there's a multitude of different ones in use. This symbol here, you see the little thing in there? It's called a hysteresis, and it goes different ways even. Pay attention to the bubble on these 4 symbols only. They are consistent. Everywhere else you see the bubble, try your luck. But here, in logic, in Boolean operations, the bubble means invert. So there's the symbols. These are the ones we're going to commonly use. We don't need the inverter. You can make an inverter out of NAND. You can make everything out of NAND. But inversion is an incredibly common operation. And, for example, in a common size chip, you can generally fit 4 NAND gates, but you can fit 6 inverters because you have 2 inputs and 1 output, 1 input, 1 output. So in this case, it's worth it to use both. But it can, in the extreme case, be worth it to literally use nothing but NAND. So let's do it. First things first, let's prove that these gates are all the gates that can do anything. Literally every possible operation. So let's say you have input 1, and let's change the name. You'll commonly see these as A and B for input 1 and input 2. So 1, 1, 0, 0. As usual, I should have drawn the line after. 1, 0, 1, 0. And then for single input, it's 1 and 0. This is the only possible combination of inputs and outputs. For single input, you've got high or low. For 2 inputs, they're both high, neither are high. One is high, the other is high. But these gates don't have a polarity on each side. That is to say, the circuit doesn't know which one is which. They're not labeled, they're not marked somehow. So it can't tell the difference between these two. It knows only that there are 2 ones, 1 1, or 0 ones. That's all it knows, because these two are indistinguishable to it. So let's write this a different way. There's always one output. So what do we have? Let's say we want to say input, output. If there are 2 ones, we want the output to be 1. If there's 1, we want the output to be 1. If there is 0, we want the output to be 1. So it's, if there's 2 ones, then it's 1, 0 otherwise, obviously. Or, what if there's 1 or 2 ones? Then we want a 1. What if there's 0 or 1? What if there's 0 or 2? So we're saying if there's 2 ones, if there's 1 1, if there's 0 ones, if there's not 0 ones, if there's not 2 ones, if there's not 1 1, then it's 1, and 0 otherwise. So that's the complete set. So what if I say I want it to be 0 if there is 1 1, and 1 otherwise? So 0 if there's 1 1, well, that means it's 1 if there's 0 or 2. See, it's just inverted, so this is the complete set. If you want 0 somewhere, you just say, well, I want 1 everywhere else. So this is all the possible operations on 2 inputs. So all we need is to pick operations that give these results, and we can do anything with 2 inputs. So let's write out some truth tables. If A is 1 1 0 0, B is 1 0 1 0, and Q, commonly the output is labeled as Q. So what do we say? Let's do AND. Well, what is the AND operation? It's if both are 1, 0 otherwise. This one and this one are true, then the output is true. Well, so now we have 2 ones give us 1, otherwise 0. AND. All right. How about OR? Well, we're just saying if one or the other. All right. Well, one or the other, one or the other, one or the other, neither. So if there's 2 ones, or if there's 1 1, we get a 1. 2 or 1, 1, or. All right. How about NAND? It's the opposite of AND. So if we say 1 and 1, but we want not AND, so 1 and 1 is 1, but not is 0. 1, 1, 1. 0 and 0 is 0, so not is 1. 1 and 0 is 0, so not is 1. So now we have 1, 1, or 0 ones is 1. NAND. Doing great so far. How about XOR? It's exclusive OR, because regular OR is inclusive. It's one or the other or both. Exclusive OR is just one or the other. Well, one or the other, not otherwise. XOR is commonly considered a flip. So if you have a 0, and you XOR it with a 1, you get a 1. If you have a 1 and you XOR it with a 1, you get a 0. So this is used often if you want to say, okay, I have 8 bits. I want bit 2 and 3 to flip and everything else be the same. Then you create something that's all zeros except for 1s in the 2 and 3. That's your mask. XOR it together and you flip bits 2 and 3 and leave the others alone. But we'll get into that later when we do some programming. Right now we say XOR. So it's 1 if you have a 1, 1, 1, but it's not 1 if you have 2 or 0 of them. So 1 is XOR. How about NOR, not OR? Well, it's just OR flipped. OR is false if neither of them are true, so we flip it to a 1. OR is true otherwise, so we flip it to a 0. It's just not OR. Well, it's 1 only if there's 0 ones. NOR. And finally, our XOR. Our XOR was 1 if they were different, but now it's 0. Remember before? It's one or the other but not both is true, but now we flip it to be false. So if there's 2 or 0 ones, we get a 1. 2 or 0, XNOR. And there you go. So now we've proven we can do anything with these 6 gates. Now we prove that we can make all 6 gates with just that one. But first we'll do the 1 input because it's quick and easy. So we have not. The truth table for this is 1 0 becomes 0 1. So how do we do that with a NAND gate? Well, let's go ahead and write the truth table for NAND up here, just so we have it handy. So NAND, if we have 1 1 1 0 0 1 or 0 0, NAND is 0 1 1 1. That's the NAND truth table. It's 0 if both are true, because that would be AND, so NAND is the opposite. It's 1 otherwise. So if I have a NAND gate, here's my input. Let's hook up the input and hook up the input. That's an inverter. So we have A NAND A. I'm going to introduce a symbol for NAND just to make it easy. It's this. I'm just going to write it like that. Don't worry about it. That way I don't have to write NAND all the time. So what do we get here? The operation we want to do is A NAND A. So A is on the left. So let's do 1 1 0 0 NAND 1 1 0 0. If you know what a vector is, this looks familiar, but that's not important right now. So we said If both are 1, it's 0, otherwise it's 1. Well, both are 1, so we got a 0 and a 0. Everything else is a 1. So here's our input, here's our output, we flipped it. So there is your NOT gate. So now that I've proven the NOT gate works, I'm going to keep life simple. If we want a buffer, because I don't have to keep proving that I can make a NOT gate. If I can do something with a NOT, you know you can switch a NAND in there. I'm not cheating, I'm just writing less. So if we want buffer, and like I said, wiring this up directly is going to be more efficient. I'm just showing you can, because sometimes you'll get just a massive amount of NANDs and you're like, well, why not wire it up this way? Because you can get a computer program to do it. You don't have to manually wire NANDs. There are computer programs that you put in what you want to happen and it'll just make all the gates for you and say, okay, do this. So maybe it's quicker and easier just to have the computer do that and have a bunch of NANDs and not worry about it. Truth table for buffer. 1 stays 1, 0 stays 0. So we have an inverter, which we've already said is a NAND gate. We can do that with a NAND, so this is a NAND still. I'm just going to save myself some writing. Please, sir, may I have another? So here's A, boop, 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 Q. So that's easy enough. Let's have a symbol for NOT. Good enough. So we have 1 and 0. That's our A. NOT, 0, and 1. We just flip it. But then we NOT it again. We flip it again. We're back to where we were. And remember, this is NAND, so we can do the same thing with NANDs. You can have A into there, and then there, and there, Q. See, this is why I'm not going to write NAND every time, because we already did. So that's the one input gates. Easy peasy. We've got a NOT, an inverter, and a buffer. Now let's get to the interesting stuff. So first of all, I'm going to eliminate 3 of them. We have OR and not OR, but that's just OR with an inverter. And an inverter is a NAND gate, remember? So whatever we have, we can just invert it. Again, there are more efficient ways to do it, faster ways, whatever, including with just NANDs. There are different ways to wire it up with just NANDs. I'm just proving you can. You can worry about making it better from there, or, even better, let the computer do it for you. This is the kind of thing computers are for. That's why we're doing all this. That's why we make them. For all the number crunching, we tell it, I want this. And the computer sits there for a day and a half and figures out the absolute best way to do it, and then you send it off to the fabricator. There you go. So we'll do AND. NAND we already have. We'll do OR. But NOR, not OR, is just OR with an inverter. So whatever we do for OR, add an inverter, which can be a NAND gate, and you're done. XOR. Well, XNOR is just not XOR. So that with an inverter. So we only need to do 3. AND, OR, XOR. The truth table for AND is 1, 1, 0, 0. 1, 0, 1, 0 becomes 1, 0, 0, 0. AND is 1. If both are 1, 0 otherwise. This is an AND gate. I tricked you. It's just an inverter, isn't it? NAND is AND, and NOT, with a NOT, gets you back to AND. We already proved that. That's a buffer. It's an AND gate and a buffer. The buffer does nothing, take it out, you just left with an AND gate. Well, that was easy. Let's move on. Let's do the OR gate. OR, we decided, is 1 as long as anything is 1. 1, 1, 1, 0. The only time OR is not true is when both are false. This is an OR gate with NANDs. So remember, an inverter is just a NAND with the inputs duplicated. So we've got 1, 2, 3 NAND gates. So what is this? We negate A and we negate B and we take the NAND of the 2. Let me put my NOT notation back. So that means we have A NOT and B NOT. Well, that's easy enough, but let's prove it. So A is 1, 1, 0, 0, 1, 1, 0, 0. But if we take the NOT of that, we get 0, 0, 1, 1. B NOT, well, B is 1, 0, 1, 0. Invert that, we get 0, 1, 0, 1. So now we're taking the NAND of that. So A NOT is 0, 0, 1, 1. B is 0, 1, 0, 1. Well, when is NAND a 1? Anytime it's not both 1. So not both 1, not both 1, not both 1, both 1. And there it is. 1, 1, 1, 0, 1, 1, 1, 0. So there's your OR gate. So you can make an OR gate with 3 NANDs. So that was the inclusive OR, the normal OR. The last one we have to do is the XOR, exclusive OR. Exclusive OR is 1 when they're different and 0 when they're the same. This is an XOR gate. You have your A and your B, and you have 4 NAND gates. Now it's getting interesting. So your A connects over to this, and your B connects over to this, but also to the first NAND, like so. The inputs are split. This output is split into there. It's a beautiful symmetry. There are better ways to actually wire it, but this is the pretty way. And then finally, we coalesce. Isn't it gorgeous? So what do we actually have? This is A NAND B. So this is A NAND B. This is the NAND of the two outputs. So if we have A NAND B, but we have A NAND B, NAND A, and A NAND B, NAND B. So if we write that as A NAND B, and then B NAND A NAND B. So this is A NAND B, this is A NAND B. This is A NAND B, this is B NAND A NAND B. And then those two results are just NANDed and you're done. So NAND of those two. So there's a little math here, but it'll be quick, I promise. So let's start with A NAND B equals 1100 NAND 1010. See? There's A and there's B. So the result of this, NAND is 0 if they're both 1. It's 1 otherwise. So they're both 1, 1, 1, 1. Unsurprisingly, that's just NAND. So that's this and this piece. What if we take that, if we take 0, 1, 1, 1, NAND, see, so that's A NAND B, NAND A. So that's 1, 1, 0, 0. Again, it's 0 if they're both 1. So there's a 0 here, they're both 1. 1 otherwise. So we have 1, 0, 1, 1. So this equals 1, 0, 1, 1. If we take A NAND B, which is 0, 1, 1, 1, NAND B. B is 1, 0, 1, 0. 1, 0, 1, 0. So if they're both 1, NAND is 0. It's 1 otherwise. So this one is 1, 1, 0, 1. And finally, we just NAND those two together. 1, 0, 1, 1, NAND, 1, 1, 0, 1. NAND is 0 if both are 1. That's a 0. That's a 0. It's 1 otherwise. And there it is. There it is. You can make any 1 or 2 input logical computation with nothing but NAND gates. And if you have NOT gates, well, that's still true. You're not going to make a NOT gate with a NAND gate unless all you have is NAND gates. If you have a separate chip with NOT gates on it, then you're probably going to have 6 instead of 4. But it could still be a NAND gate if you wanted. The universal gate. And as I said, there are other gates you can do this with, but this is the most common because it's the easiest. Simple to wire, simple to understand. If you're a hobbyist just messing about, you can do what I did. I bought a combo pack of logic chips and a few other chips. I'll go through them in future videos. And in there are chips that have OR gates, XOR gates, and whatnot. But I'm only going to have one of each of those chips, just in case, just for faffing about. But I'm ordering an entire extra set of NAND gates and NOT gates, inverters. If you see a standard chip, you might see 6 NOT gates. That's called a hex inverter. Hex referring to 6 of them, like hexagon. And that's going to be my logical go-to if I ever need to make a more complex circuit. I'll just do it with the NANDs, and I won't have to mess with it. Someday, we'll get into FPGAs, and we'll really understand the joys of logic gates. But until then, be seeing you.